So let's start the event. Particle swarm optimization is yet another study taking inspiration from natural phenomena of nature's wonders. Although initially developed in 1995 by Kennedy and Eberhard by simulating biological phenomena of flocking and schooling of fishes, it has been gaining a lot of traction since then and has been a talking point for researchers now. Hi, I am Ayush Acharya, Microsoft Learn Student Ambassador Nepal 2020-2021, and today I'm going to be talking a little about this effervescent topic. So, what are we going to do today? I think it's better if I talk a little about the prerequisites of AI because this is a topic that has been gaining a lot of traction in AI, although it can be used in anywhere. So, I'm going to talk a little bit about agents in AI. I'm also going to be talking about multi-agent environment and stochastic environment and how particle swarm optimization is both of those. I'm going to start then introducing a little about swarm intelligence, how ants work together to find their common goal, and similarly, how particle swarm optimization takes inspiration from swarming theory. Then, I'm going to give a little concept about PSO through an example, hopefully to make you understand. Then I'm going towards the vector diagram where I'll be deriving the formula for particle swarm optimization. Then I'm moving towards the algorithm, the nitty-gritty stuff. Moving on, I'm going to talk about the variations of particle swarm optimization because it has undergone a lot of changes since its inception. Then finally, I'll be demonstrating some code in R because it's important for you to visualize how particle swarm optimization works. And so I think this visualization is necessary. So now moving on. So I'm going to do all of the coding and demonstration in R, but I will make sure that you can implement it in any language. And so I've also provided the pseudocode in the algorithm. So hopefully you'll be able to install in any environment. But now let me show you. You can download R for Windows from the CRAN R project organization. Obviously, if you have any other distributions, say Linux or Macs, then you can also download it from the same website. RStudio is the recommended IDE by R and CRAN projects. RStudio is available in both Linux and Windows and is free. And of course, there are pro versions as well. Now, RStudio supports a lot of packages and it's usually used by R developers, but there is another IDE which I used from time to time, which is Visual Studio. Now, Visual Studio IDE is used, a general purpose IDE, I should say, because it's used for a lot of languages, and it's if you get familiar with Visual Studio, I think, and if you already have Visual Studio, I would recommend using Visual Studio. But the only reason I didn't use Visual Studio is because RTVS, that is our tools for Visual Studio, is still in preview mode for 2019. Visual Studio 2019, so I haven't used it. It's also very useful for SQL Server. Obviously, there's VS Code too, but it's just a text editor. So obviously, its powers have gone since then. So this is the RStudio IDE, how it looks. Here's the workspace that I'm showing you right now, and there's this code. I think I've zoomed it a little. we can obviously transform the windows. As you can see, there are a lot of packages that's loading. This is the code for PSO right now. I'm not going, if you are, don't be overwhelmed because I have shown you the code right now, because I'll be explaining all of them in a moment. The RStudio has a lot of key bindings, which I'll be talking about later. But before that, let's move towards the console. Now, console is, I think, a great feature of RStudio, because say if you run the program, if you run the above program, and if you have some debugging to do, or some testing that you want to do and test the code, then all the variables are already loaded in the environment, which you can see on the top right side. And similarly, you can code there, like I've shown you, in the variable a being a vector, and then the variable a, which is already loaded in the environment, you can see, and all the variables, other variables that are in there, already loaded because the program is already done. Then in the menu below, you can see the plots and views, and obviously you can always minimize it if it fits your bill. So that was the project setup and installation of R and RStudio in Windows. And while it is happening, if you are still installing, let it be, because we are moving on to the workshop, and hopefully when it finishes, we can talk about it. So this is Rstudio Cheatsheets, because when coding, you don't use the mouse too much. You can always use key bindings, and I know you cannot see very clearly here, so I have provided the link, and all of these files will be available. I'll make it available to you through Teams or through through the description. So you can always use these key bindings. And RStudio Cheatsheets, I hope that somebody would have told me about this, because it's a very important tool. RStudio Cheatsheets is available not just for key bindings, but also for machine learning algorithms and other data science tools. So you don't have to browse through documentation. You can clearly see everything in a single page, and so as to make you remember everything. So other useful cheat sheets are there in the packages. So now moving on, I will be talking about a little bit about agents in AI. So agents in AI is one of the prerequisites. Here I'll be talking about the definition of agent in AI, how multi-agent environment works, and stochastic agents. Obviously, there is a lot more to it than just that, but I'll be talking about that much for now, because it's just a prerequisite towards the PSO algorithm. So we are not focusing too much on that. So what is agent in AI? An agent is anything that can be viewed as perceiving its environment through sensors and acting upon that environment through actuators. So, without going too much into the ergonomics, say, take an example of yourself as human. Say, if somebody pinches you, and what is the natural reaction? So maybe you give a big stare to the person, no? So how does that happen? So I'm going to take you through the actions. You get pinched, and you feel the pinch through the neurons, maybe through the nervous system, and your sensory organs then send it towards the brain. Now the brain maps the sequence of actions. Say it is a pinch, so what do you have to do now? So it sends the actuators through the eyes, and the brain instructs the eyes to give a great stare. I think it moves the head a little bit towards the person facing you, and it gives a dead stare. So yeah, that is how you perceive. So this is a similar example. Now I want to show you the agent function that I had told you in the previous slide. Sorry for the translation, because I just translated it from the internet. What I'm trying to say is I am fine, how are you in Japanese. So say if there is a translator and he sees I am fine. Say suppose he sees how are you in Japanese, he perceives the sequence to actions which is called the agent function, and he replies I am fine, how are you. So let's talk about multi-agent environment. Now, how do we distinguish between agents and entities? Because in environment, both of these can exist. How can we it's very clear, I think, if we have a single agent, but if there is if there are multiple agents, it's a little bit difficult to distinguish. So in a multi-agent environment, entity B's behavior is best described as maximizing a performance measure whose value depends on agent A's behavior. So say suppose there is an entity, say B, and what B is trying to do is he's trying to maximize his own performance. And how is he doing that? He's doing that by something. He's doing that and he's also depending upon another agent, say A's behavior. Then that is called a multi-agent environment. So there are two types of multi-agent environment, that is cooperative and competitive. So say if you are playing chess, then what both of you have in mind is trying to win the game. So if one of the opponent player makes a move, then he's maximizing his own performance while also minimizing yours. But say suppose in a bus driving environment where you are maximizing performance measure is having no accident, then the environment that you are working on would be a cooperative environment where all of your actions depend upon if you follow the traffic rules. Say if you all follow the traffic rules, then you are more likely not to have an accident. So what is stochastic environment? Similar to the bus driving example, I'm going to take the bus driving example again. So let's read out the definition first. If the next state of the environment is not completely determined by the current state and the action executed by the agent, with the uncertainty about outcomes quantified in terms of probability, then it is statistic. Then it is stochastic. That meaning that it would depend upon the random values, and if it is quantified in terms of probability, then that would be it. So let's talk about swarm intelligence now. Swarm intelligence, it's a relatively new area in the artificial intelligence, which the essential part is the cooperation between agents. So if similar to the bus driving example, if you cooperate between agents and you have some method of communication between agents to find the greater goal, then that is called swarm intelligence, and that global behavior is called swarm intelligence. So the root of particle swarm optimization and other swarm intelligence algorithm is that you yourself and as an individual are not so doesn't have that global intelligent behavior, but collectively you can search towards, you can find the greater goal. So say if a school of fish collectively are in search of food, then that is called a global, finding a global behavior optimum, because one individual fish could never do that. So that is the concept. Now let's talk about a concept and vector diagram. Now, because it's very difficult to visualize this, it's very difficult to understand this at the first go, I have taken an example. So say there are two submarines, that blue one and the red one, as shown in the video. And let's say if those two submarines, uh, communicate through each other through the satellite, and the goal of these two submarines is to find the greatest depth. Say Mariana Trench hasn't been found and they want to find the deepest part of the ocean. So one of them is starting through, say, Japan, and one of them is starting through the United States, and they are searching through to find the Mariana Trench. So here what happens, the depth d2 is greater than d1. Red tells that d1, I think it's more likely that you will find the deepest part of the ocean here. So blue moves a little bit towards the red submarine side. So look, he moves towards a little bit towards the red submarine side. So obviously, because the first part that you search would probably not be the deepest part of the ocean. So bleach just moves a little bit towards red side and not completely towards the first thing they find. So now blue measures again, and he finds that D1 is greater than D2 at that moment of time. So he again talks to the green satellite and tells it, yeah, now I think I have found a deeper spot than you have. So why don't we move a little bit towards my side? So this happens again. So red moves towards blue a little bit. And this is the cooperation between agents or particles. These submarines, they can be viewed as particles. The D1 and D2, that is the depth, can be viewed as a performance measure. And that red spot that I've just highlighted there in the bottom, that is the deepest part, probably the deepest part. And the ultimate goal is finding the deepest part of the ocean, and hopefully they will find it. So that is the part that I wanted to show you, that is the cooperation between agents and how these agents interact with each other to find the common or the goal. So particle swarm optimization, it was initially developed to find the so it was initially developed to find the non-optimized nonlinear functions. So say the blue dot or the blue colored dot, it would, let us assume that it is a particle. So its current position can be given by x, I, z, t, where I is the number of particle and j is the number of dimension. So t is the time at that instant. So green color is the global best, meaning the best position among all the particles at that moment of time. So initial velocity is VIJT, and cognitive component and social component I'm going to be talking about before, which I'll explain what is red color. That is personal best. Okay, so that is in among a number of iterations, that is the personal best position of that particle. Okay, so that is the green and red part, which is the social and the cognitive component. So what it is called, so I talked about the submarine example where I showed that if you find the first place, say the red submarine found a deeper part of the ocean than blue. So if you straightly go towards the where the red submarine is, you are more likely not to find that part. So what do is you interpolate between your personal best and the global best to maybe in the hope of finding something that is between that. So what do? You go a little bit towards your personal best, which is called the cognitive component, and you go a little bit towards the global best, which is called the social component. Now, the original PSO algorithm, what it did was that it had two parts. One is finding the global best, which I'll be talking about here, the algorithm, and one is finding the local best. So the difference between the global best and the local best is that the the social component is lies in the social component. Okay, so the difference lies in the social component, and what it does is that the local best component that exists, it will be among the nearest neighbors of that particle, the blue particle, that is, it will be among the nearest neighbors of that. So so the social component, so the society that blue lives is different, and that is the difference between the local PSO algorithm and the global PSO algorithm. So you move a little bit towards your initial velocity, that is called the inertia term, and you move a little bit towards the cognitive component, and you move a little bit towards the social component, and R2 and C2 and R2 and C1, so sorry, that cognitive component should be C1. I made a little bit of mistake, R1 and C1. So if you move a little bit towards your personal best and the global personal best, then you will probably find some place where it is an optimum solution. So that is the main thought process behind particle sum optimization. So let's talk about the algorithm and hopefully you'll be clear. So in this algorithm we have say select an objective function f x1 to xd minus 1, which is with d dimensions, of which the global optimum is to be found. So I think it's better if we talk with an example in this algorithms. So let us select an objective function y is equal to fx equals to x squared, which is a parabola. I think it's a familiar function to all of us. So it is a two-dimensional function for which we want to find the global optimum. So we all know that the global optimum or the global minimum of this parabola lies at 0, 0. Okay, so this is a common example, and I think everyone knows this, that the global optimum, we can easily visualize this. But what about 5-dimensional vectors? So it's very difficult, it's impossible, I would say, to visualize a 5-dimensional vector. So in that case, particle sum optimization, it doesn't require the nitty-gritties of derivatives, the complexity that arises with it, and it works for any dimensions, any d dimensions. So that is why this algorithm is important, because it's not just optimizing for a two-dimensional function, it's also optimizing for 5-dimensional or any dimensional function. So that is important, but for this example I'm taking a two-dimensional function. So moving on to the next point in the algorithm, so let's determine a range of variability for each dimension. So that is called, so because this is an objective function, y is equal to x squared, so the range of y is equal to x square is somewhere from negative infinity to positive infinity. So that is a lot of search space. So the thought process of particle sum optimization is that it it initializes a certain value in the search space. So if you keep the search space as negative infinity to positive infinity, that is not good, and you have to initialize a lot of parameters. So you maintain a certain search space and you initialize the random particles there. So you determine the PSO parameter values, number of particles, the acceleration of the cognitive component C1, the acceleration of social component C2, the number of iterations, and you create a d-dimensional G-best vector because there are d-dimensional particles, and then the solution is d-dimensional, and you then initialize p search space with random particles initialized. So this is the main part of the PSO algorithm, I would say. So there is a bit of variations among the researchers. Now PSO algorithm has undergone a lot of research, and I'm only telling this about the original PSO algorithm. So the initialization of values goes like this: for each ith particle pi from swarm P, create a p-based particle equal to the ith particle. Okay, so I would just tell you the difference between other variations and this. So first you initialize all the particles velocity to 0, you initialize all the particles position to random values in the search space. So the in other algorithms, in the variations, you initialize the particles to not just random values, you initialize particles velocity to random values, sorry, and not 0. So obviously the formula is same from the vector diagram, and you always check whether the particle has arrived in its best position, and the particle has similarly is you in every iteration you check which is the best cost, which particle provides the best cost, and that would be the G best factor. So let's talk a little bit about variations in PSO. So the original PSO algorithm, if you have noticed, has it always adds off velocity. So this would slowly cause the exploding velocity. So the exploding velocity is one of the main problems of PSO algorithm, and that is why um, a lot of variations have come along, and all of these variations that I've stated here are trying to solve that exploding velocity problem. So let's talk about the first velocity problem, velocity clamping. So what this would do is we would set a certain threshold Vj max, and if that velocity crossed over Vj max, then we would set it to Vj max. If not, then the velocity would remain the same. The Vj max would be calculated through the two formulas below, which one of them is through the generation, that is T generations, calculated through generations, and the next one is calculated through search space. So that is how PSO algorithms worked. So let's talk about inertia weight. Inertia weight is what I used and most of us used. It's some value between 0.9 to 0.4, and that is how that is decreased over time in the number of iterations. Constriction coefficient is also one of those that is used, and you can always see the formulas here. Bear in mind that constriction coefficient phi 1 and phi 2 should the sum of constriction coefficients should always be greater than 4. So now let's talk about the acceleration coefficients. So acceleration coefficients, they govern how the PSO algorithms work, and they are the social and cognitive component of the PSO algorithm. So there are obviously four cases for which of four different values for PSO algorithm, or sorry, for the components. So C1, if C1 is greater than 0 and C2 equals to 0, that's cognition only modal for PSO algorithm, and similarly social only modal for PSO algorithm. So what is unimodal problem? Unimodal problem is those problems which have only one peak, which can be seen in statistical distributions. So so obviously it would make sense for the social component to be more suitable for one mode and the cognitive component to be suitable for two modes. So now let's just proceed towards the code demonstration, and we will then move on towards the QA session. So moving on to the code demonstration in R. So in R you require certain packages similar to uh, all other libraries, all other languages. So I have listed the required dependencies in comments. Similar to Python modules, you also require some packages in R, and these packages, Pacman is an easy package manager with loads. So what RStudio offers is executing line by line code. So control enter is how you would execute that line. So if you select a certain line and then execute it through control enter, then that line would be executed and it would show up in the console below. And what it would do is that it is already loaded, so you can always try it out in the console. So this is the y is equal to x square function. So if y is equal to 4 square, it should return 16, and yes, it returns 16. So what we have to do now is we have to set up the parameters and hyperparameters. So I've made the search space x as -10 to 10 and search space y as -10 to 10 as well. Similarly, the iterations are 90, and I've sent the w, or inertia weight, that is a variation, as something that would decrease from 0.9 to 0.4. Similarly, I've sent the C1 0.5 and C2 0.5, the acceleration and acceleration component and the acceleration coefficient of the cognitive and social components. So, uh, so let's see how W would decrease in the console. You can see that it's decreasing step by step, and SEQ is called sequence, and that sequence function is very useful, I think, in R. So R supports a lot of packages, and a lot of packages uh, they they expect you to store all the data in the data frame, especially the ggplot package. And what is a data frame? Data frame is similar to a table or a relation in database where attributes are stored in column and they are a relation. Each attribute is a relation and is independent. They require having unique names, and the data frame particle is being stored here. So I've initialized the values. This is the initialization stage. So they are initialized to random values in the search space. You can see the position X and position Y. The velocity I have initialized to 0 according to the original PSO algorithm. The curve position X and curve position Y is for the parabola, which is from so it's just a random value from, it's not random, it's minus 10 to 10 values of X and the value that is returned from Y. So that is how much. Now time to initialize the best cost, or particles best cost and particles best position. So now I've calculated, now that I've initialized the particle's position, I can calculate each particle's best cost, which would be the same cost that it has now. Then I can also initialize particle's best position, which would be its current position, obviously. And this is now, it would make the calculations a lot easier now. Now, obviously, there is the need of having the best position. There is the need of having the global best. So obviously, there is the need of the global best now. So I just wanted to show you which particles now. I just wanted to show you that the different values of the particles cost, and hopefully you found the minimum one. I think it's somewhere about 1 point something. That is, yes, the global base cost is 1.74, and obviously there's no need to store it in the data frame every time. It's actually redundant. It's not a good programming practice, but I just wanted to make it clear for you so that you understand. So for every iterations, I have stored the equivalent global best cost. So now we move on towards the main loop, the iterations. So we iterate until we find the global best, obviously, but we have set a finite number of iterations now. So first we calculate the velocity according to the formula that we had told. Then we initialize the next position of the particle. Similarly, we check for the search space constraints, and that would be if the position is out of the search space, then we would set it to the search space boundary. Next, we calculate the particle's best position, and we then we add to the data frames. So in each iterations, we add the newly calculated value to the data frame, which is just a table that I showed you earlier. So let's run this iteration. It might take a little bit time, and hopefully it won't take so much. So obviously you can see the you can see what has happened in the right side, where there is environment and the variables that are loaded. So let's move on towards the data frame. So what you would expect to see is that the global best cost, that is, it should be decreasing. And what is the global best cost? It's the calculated value by the particle swarm optimization to the uh, to the actual value that is obtained from the objective function. So the difference between those absolute value and the difference between those should always be decreasing. So look at that, it's already in the range of 10 to the power minus 5, and finally it is in the range of 10 to the power minus 6. So we told that it should be 0 0, the position should be 0 0, and look at the global best position, it's near to 0 0. Okay, so now you can see that it's near to 0 0, the best position. So our algorithm is working. Now it's time to visualize. So I've used GG animate as plot, and also used I've used GG animate as plot. And so first, the density 2D field that I've shown you, just for it's just for plotting contour plots, which is for higher dimensional functions. So right now I'm going to be plotting a line that is just the line of the parabola and show you the particles. I've used GG Animate package, which is a great interactive package in R, and I love using it. It's very convenient to use. And right now the iterations are happening. So some things I have missed out, I think, to tell you is that R1 is a random value between 0 and 1, and R2 is similarly a random value between 0 and 1. C1 and C2, they are the coefficients, acceleration coefficients, C1 being the one of cognitive component and C2 being the one of social component. Um, so obviously R1 C1 multiplied by the P best minus the current position would give you the cognitive component. That is the part where you would like the particle to move a little bit towards the particle's best position. And similarly, we have the global best position social component, which is R2 C2 multiplied by global best minus the particle's current position, which would be the G best position. So now what I would like is to see the animation. And before that, that's animation is being loaded. Uh, Bear in mind that the frame rate is very slow. My computer is being a little old now, and the animation might be a little slow. Hopefully over time it will be clear to you what is happening. So by iteration count, you can see that the particles are converging towards one spot, which is the global optimum spot. And this animation is beautiful, but maybe what would you do for a higher dimensional function? So this is what you would do for a higher dimensional function. This is a contour plot. This is not a contour plot, this is a density plot, which is similar. Which now in this density plot, you could see the bright yellow side, which would indicate the global maximum or minimum position of a plot, and the particles, they seem to be converging at that point through particle swarm optimization. And it's such a simple algorithm. So if you have any questions, you can drop it below, and the files will be made available through Teams and other descriptions. So thank you everyone.